Jean-Philippe, can you share the screen? Yeah, okay.
Yeah, it works.
Yeah, it works. I can see slides. Okay, ladies and gentlemen, it's an honor to introduce the first speaker of plenary talks in the recap conference, Professor Jean-Philippe Lessard. I would like to introduce a bit his history. Jean-Philippe Lessard is an associate professor at McGill University since 2017. He obtained his PhD from Georgia Tech in 2007 under the supervision of Konstantin Mishaikov. He spent some time as a postdoctoral researcher at Rugeter University, at UBU University at Amsterdam, was awarded a fellowship from the EAS in Princeton, and was a group leader at the Basque Center for Applied Mathematics. He then became a professor at the Laval University, where he stayed for 6 years. In 2016, he was awarded the CAMES PIM's Early Career Award in Applied Mathematics and was CRM's deputy director of scientific program from 2019 to 2021. In his research, he combines numerical analysis, topology, and functional analysis to study finite and infinite dimensional dynamical system. As you know, he is a very active researcher in this field, and maybe you may know his names for every papers. So, and it's my pleasure to have his lecture in the past plenary talks. So Jean-Philippe, please start as usual.
Thank you so much, Akitoshi, for the wonderful introduction. It's a pleasure to be here. It's an honor, in fact. I would, of course, have preferred to be there in person, but I think we are slowly getting back to normal. So today I'm going to talk about something which I'm not used to talk in general. I'm quite honored to be giving a talk about the parameterization method. In fact, I was asked to present kind of an overview talk about it, and I was delighted to accept. But it's the first time for that kind of talk for me. So I hope you will enjoy. All right, so what I will talk about is parameterization method, and the idea of that approach is that it is a method which is very versatile. It has already a rich history, and it's applied to understand mainly invariant manifolds. Okay, so why invariant manifolds? Well, often they act as organizing centers, right? So if you think about a phase space and you have some invariant manifolds, and they can actually partition the phase space of a dynamical system in a nice way. So just an example here would be, if you look at the global attractor in the Lorentz equation, and then you think of that beautiful object here, which is the stable manifold, which has been globalized, then it partitions the state space of the Lorentz equations. And that's coming from a Multifario, which is a software developed by Michael Anderson at IBM. And also what is very important is that the changes in the invariant manifold, the stable and unstable manifold, and their intersection, when we vary parameters, then they give rise to global bifurcations, which are often very hard to grasp using local perturbation techniques. So these objects are quite important. Moreover, for instance, a very important result is Smale's Tangle theorem, which says that if you have a transverse intersection of stable and unstable manifolds of periodic orbits, that gives rise to a horseshoe and therefore chaos. Okay, so that's kind of these are just few of them, and maybe a last one, which is not necessarily linked to say intersection and bifurcation. It's more the fact that they're useful in design of low energy transfers in celestial mechanics. There have been special missions where, in fact, I think there's a very famous Japanese mission which was using the energy of the manifold to actually save some mission. I would have to look at the details, but I remember reading about it. And okay, so these are just general motivations. And because they're so important in practice and in the theory of dynamical system, it is not surprising that there's been a lot of computational techniques to develop to understand and to compute these objects, right? So going back to some work of Guggenheimer and Workfall in 1993, they developed a geometric level set method to kind of globalize manifolds. Same thing, similarly, on a similar approach 4 years later, Johnson, Joly, and Kevrekedis, they use some sort of arc length representation of the manifold, and then they also use that to globalize manifolds. Then different algorithms, Delnitz, which was kind of a box covering algorithm to really kind of get a rigorous outer approximation of some invariant manifolds using Gaio. That's pretty early work. Then Kalapskov and Osinka wrote a couple of papers where they kind of built from the work of Guggenheimer in 1993. And then I talked already about Henderson. So he was developing, and he still is developing this multifariate computational software, which kind of it's integrating fat trajectories, and it's intersecting with surfaces, and it's kind of building in a nice way some invariant manifolds, but again with the goal of globalizing them. Similarly, Guggenheimer and Valimirsky, they introduced a PDE formulation, which is not exactly what the parameterization is about, but the parameterization also introduced a PDE, but that's a different one here. But the PDE formulation here imposes that the vector field is tangent to the graph of the manifold, which, as you will see, is kind of similar in spirit. Finally, not finally, but Whiting, Burtz, and all, they also studied how to globalize manifolds with Taylor integrator. And then other methods, Roy and Vrobel, they developed a high order bisection method for maps. Vrobel and Goodman in 2013 for discrete dynamical system via what they call the quasi-interpolation method. And maybe the last one that I will just mention briefly is that Haller and all have been studying the spectral sum manifolds, which are really corresponding to what I will talk about today, and they have their own techniques to compute. So as I said before, most of the first references are mainly there to obtain global manifolds, to globalize them. So what they often do is that they start with a local linear approximation of the manifold, and that's the starting point for applying their machinery. Okay, but then there is the parameterization method, which on the other hand, what it does is that it spends a lot of time locally to get a very high order approximation. And not only this, but then we have something more. We have what we call the conjugacy. I will talk about that briefly. But before talking about that in more details, I would like to present a little bit of the foundations of the method. Okay, so it goes back all the way to the seminal work of Cabret, Fontich, and Dalayave. These three papers from 2003 to 2005, and they focused essentially on the presentation on stable and unstable manifolds of equilibria and periodic orbits in ODEs. Okay, of course, after that, it became much more broad, and it was applied to different type of systems, but that kind of is the ground of their approach. And then after that, for invariant tori, Alex Harrow and Raphael Dalayave wrote also three papers not so long afterward, where now they generalize that to invariant tori. So these are really I would say the foundational papers that gave rise to the whole world, the parameterization method. And in this talk, what I will do is that I will essentially focus on one example, which will be kind of inspired by these two papers, and I will present in details the approach for stable manifolds of equilibria of ODEs. Okay, and then toward the end, I will present some examples for delay differential equations and partial differential equations. But the presentation, since I would like that talk, I wanted that talk to be an overview, then I'll stick to the simplest possible case. All right, and before I want to do a little bit more presentation, so I want to emphasize that the world of computer-assisted proof and the parameterization method has been like working together a lot, right? And then in fact, I have one of the world experts in on Zoom right now and in my apartment, Jason Mireles James, and he's the one who introduced to me all of that. And we started to work together in a conference in 2009 in Poland. And that really is where I started to be interested in these invariant manifolds, parameterization method, and so on. So I want to give a little bit of an overview of what has been done for computer-assisted proofs and the parameterization method. So just some references. There are much more than that. And I apologize for those of you who are yeah, I mean, do not appear there, but there's been quite a lot of work. So I started, as I said, to work with Jason Mireles James in 2009, and then we published a paper with Vandenberg and Mishalkov, where we wanted to compute homoclinic orbits, and for that we actually did use the parameterization to get the stable and non-stable manifold, and we solved the projected boundary value problem. So by plus caps, I mean plus computer-assisted proofs. And then Jay and Constantine, they developed unstable manifolds, stable and unstable manifold and connecting orbits for analytic maps, also with computer-assisted proofs. Very nice paper by Renato Calleja, Seletti, and Delayavi in 2013, where they studied KM theory for conformally symplectic maps. Then we, together with Roberto, we introduced a method to do Fourier-Taylor parameterization of stable and unstable manifold for periodic orbits in ODEs. And then there was this wonderful book by Alex Harrow and all, literally on the parameterization method, and they also present ways to make these computation rigorous with the fast Fourier transform, with interval arithmetic, and there are lots of beautiful tricks there. Then Jay and JB, Jan Bauer Vandenberg, Christian Reinhardt, they studied manifold when there are resonances. I won't talk much about resonances today, but when they're there, the approach that I will talk about today won't work because an operator is not invertible. But when they're present, then there are ways to actually adapt this method. So that was done together with computer-assisted proof in 2016. And then a method based on say invariant vector bundle to actually compute slow stable manifolds was introduced as a numerical paper, but there is hope that this will be used for, say, compute slow stable manifold of PDEs. When you think about a steady state of a PDE and you want to compute a connecting orbit, then there are the slow directions or the fundamental ones to understand, and this paper proposes ways to actually exploit that feature. Then Jay and Chris Rutede in 2017, they introduced how to compute numerically parameterization for unstable manifold of delay equations. And then in 2017, Jay and Maxime Murray did the Chebyshev-Taylor parameterization of manifold for periodic orbit. They used the fact that they could, I mean, they kind of took they took the presentation from 2015, 2018, and then they did, instead of Fourier in time, they did piecewise Chebyshev and Taylor in say the normal direction to the periodic orbit. And then this is a fantastic paper where they grew atlases. Shane Kepley, Bill Callis, and Jay, they grew atlases by doing this analytic continuation. And you should look at this picture of the Lorentz the Lorentz stable manifold, which is now enormous, and it's all with computer-assisted bounds. Then manifolds of equilibria of one-dimensional PDEs plus computer-assisted proofs were presented in 2019. Manifolds in connecting orbits in the circular restricted three-body problems. Finally, there is this new and recent numerical paper where they studied unstable manifold of standing waves on the line. And Jan Bauer Vandenberg, Wouter, and Bob Rink, they did recently a nice paper on center manifolds. It's yet to be put all in the rigorous footing, but I think that JB will talk about that, where we'll, I mean, in his talk about the spiral waves exploit this, and I think he has computer-assisted proof. So I should put probably a plus CAPS here with a question mark. And Olivier Hainaut, my PhD student, and Jay and I, we recently did this unstable manifold for DDE. So building on the work of Chris and Jay in 2017, and we put that in the context of computer-assisted proofs. Finite element approximation of invariant manifolds were presented in 2021, and maybe a last one, which is really more toward the applications, is this application to reduced order models of finite element nonlinear structures. Okay, so I know it's a lot, and there's quite a lot more, but I wanted to present what has been done since we started to combine the parameterization with computer-assisted proofs. There's a lot of work prior to that, which was numerical and beautiful, but yeah, I just don't have time to present all of them here. All right, so as I said, what I will do now is that I will focus on the simplest possible setting, at least for me, which is about looking for stable manifolds of steady states in ODEs, equilibria. Okay, so that's the setup now. I'm considering x dot equals f of x. That's an ODE. F, I'm assuming f to be smooth. And I have a flow. I'm assuming without loss of generality that it's defined for all T in R. Could just take a topological conjugacy to a topological equivalence to define it on the whole R. And I'm taking X to be an equilibrium solution. And I define a stable set. I don't want to use manifold here because it's a little bit of a misleading word. The stable set for X tilde is defined to be the set of all initial conditions in Rn, which limit as time t goes to plus infinity to the steady state. Okay, and why it is not a stable a manifold per se? Well, here's a simple example where you'd have two steady states here, and then when you think about the stable set associated to X tilde, then you have this segment here, but then the whole homoclinic orbit is part of that stable set. So that is really given by a loop, and then there's a small little piece of branch which is attached. So locally, this is not a one-dimensional manifold. Okay, but on the other hand, you can say, well, it's not so nice because if I want to compute, I would like to have nice representation of how to compute them, and in higher dimensions, would like to be able to use, say, I mean, we'll be using Taylor, but if you want, oh, is there a question? Yeah, just hear something. Okay. So how to handle that? Well, then we define the local stable manifold, which is now really a manifold, and that's the set of all initial conditions in the stable set, such that the forward orbit of the point will remain in that set U. So if I take a set U here, then I take all points in the stable set, then the only pieces that will remain with the forward orbit, so that's the forward orbit here, in that set U, are only given by this subsegment there. And that's a manifold. Okay, and that's what we're aiming to compute with the parameterization method. Okay, so local stable manifold. So let me put a little bit of a background here, or some assumptions. So I'm assuming that X tilde is a hyperbolic fixed point. So there's no eigenvalues on the imaginary axis. I'm assuming that there are m stable eigenvalues. So f, now keep in mind it's in Rn, so m is less or equal than n. Okay. I'm assuming, for the sake of simplicity of the presentation, that the lambda i's are real and they have associated eigenvectors. Okay, so if I have complex valued if I have complex eigenvalues, then this method can be generalized. It's just a little bit simpler to present in the context of a talk like that. Okay, then I have m stable eigenvalues. So I build this m by m matrix with the stable eigenvalues on the diagonal. And I built my matrix AI, which is now n by m, which is the matrix built from taking the m stable eigenvectors and putting them in the columns, right? And what I will have is that now I will show you the fundamentals of the parameterization method, which is to kind of assume that we have a conjugacy on the manifold the dynamics on the manifold is conjugate to the dynamics in parameter space, which will have the dimension of the stable eigenvalue. I mean the stable eigenspace, and in that case it is m. So the linearized flow in parameter space will be the following. So it's just going to be e to the lambda theta, which is the standard exponential solution. So that's the associated flow of that ODE in parameter space. Okay. So here's the idea. So what I have at the bottom here is that I have parameter space, because the method is called the parameterization, right? So we want to build a map that will go from parameter space to state space, whose image will give us the wanted local stable manifold. Okay, so then I start first by understanding what's happening in parameter space. So I start here and I say, well, I will take a theta in my space. And then I want to map that theta in Rm. So if there's one stable direction, then m equals 1. So there's just, it's not a disk, it's just an interval. Could be in a higher dimension. So I take that and I take the image, okay? And what we want is that image, we want that image to be on the local stable manifold. So that P of theta here is on that object, okay? That's what I want, right? And then once I'm on that, what I can do is that I can flow forward under the flow of my ODE. And then that's basically, that's the do you guys see my arrow, right? Okay, so that's my the direction of time here. So this is P of theta and I flow forward and I get somewhere, right? So this is one path, but then the parameterization needs to satisfy the other direction. So if I actually start from parameter space and now I flow with the linear flow e to the lambda t, I start from theta, I evolve under the linear flow or the exponential, and then I get that point, which is e to the lambda t theta. And now I apply the parameterization to it, and I want to get at the same point. So basically what I'm asking is this conjugacy relation here. I want that the flow of, the phi of t, p of theta equals p of e to the lambda t, which is the second path that I took. Okay, and that's the condition I'm going to impose, and p is my unknown. So I want to solve for that function. So that function will be a function defined on some disk in Rm. So typically we take it to be the unit disk, and because we can play with some rescaling, which I will mention briefly. And that's a function that goes from the unit disk in Rm to Rn. Okay, so that's our unknown, and that's the relation that we're going to impose to it. Okay, so that's how we're going to solve for it. So to be a little bit more precise, so we look for a map P, which satisfies three things, right? So first we want the actual, so if you think of 0 in parameter space, 0 in parameter space is the unique fixed point of the linear dynamics theta dot equals lambda theta. So we want that fixed point here to be mapped to the fixed point at which the local manifold is attached, right? So that's the first requirement here. P of 0 is equal to x tilde. And then it's a manifold, and it's a stable manifold, so it better be tangent to the stable eigenspace. So then if you go back here, so well, I didn't put the tangent space, but we want the derivative of the parameterization at 0 to be tangent to the eigenspace. So by the notation that I use, so basically A0 again was the matrix with the columns being eigenvectors. So then I impose that dp at 0 is equal to A0. So these are my first order constraints. And then I impose that conjugacy relation, which I introduced before. And for those of you who know the Harmonic theorem, so that's kind of reminiscent of this one, because Harmonic theorem says that if you have a hyperbolic fixed point, then on the full neighborhood of the fixed point, then the dynamics of the nonlinear equation is topologically equivalent to the dynamics of the linearized system. Now it's very similar, but now we are only asking that conjugacy to be true on the stable manifold. Okay, so that's kind of that's the same idea, but it's just on the manifold itself. All right, one remark. Oh, sorry. Yeah, is that the image of P is actually, so if I take the image of the ball under P, then I'm going to get the local stable manifold. Why? Because think of P of theta as, so if I do have this satisfied, then P of theta here, and I take the limit when I take the flow of the forward image under the flow of P of theta, then that's the same as, because of 3, it's the same as the limit when t goes to plus infinity of P of e to the lambda t, which, well, of course we need regularity, but we will be solving P in a class of analytic functions, which will make sense if F itself is analytic, the vector field. So we'll be able to pass the limit inside, and that's going to give us P of 0, which is x tilde. Okay, so if we can build P satisfying these three conditions, then we do have that the image of P under the image of the ball is in fact the local stable manifold. One thing which is important to realize is that this This is not so practical. Equation 3 is not so practical because it requires computing the flow. It has the appearance of the flow, which is not known explicitly. We have it for the linearized flow, but not in general, right? So we would like to introduce something which is more practical. And that's part of the next slide, which is the parameterization lemma, which basically gives us the following.
May I ask a short question?
Yes.
So what you showed on the previous slide is actually that this mapping P maps into the stable manifold, right? But
yeah.
But why is it parameterization? So why is it onto, so to say?
Right. Yeah. And I mean, this I didn't put, but it's quite easy to actually show that it is onto using the fact that it's that the dynamics in the linear space is actually invariant, and it goes to zero. Right. I could do that proof that here you're right that it implies only inclusion, but after that I can prove easily that it's onto.
Just by dimension considerations, right?
By dimension consideration and by the fact that if you assume that you have it maps 2 points to themselves, then you can actually flow backward. You can use the linear flow to actually arrive to a contradiction, and it must be the case that P is onto.
Okay, thank you.
Yeah, but I could give you yeah, actually I wanted to avoid that, but then you very good, Michael. You picked it up. Yeah,
So
but
please go on avoiding it. It's okay.
Okay. And very good catch. All right. So so I want to present I want to reformulate equation 3 in order for the computations to be kind of easier, right? So here's the parameterization lemma. So if P is smooth and it satisfies 1 and 2, then P satisfies 3 if and only if P satisfies the following PDE, which, okay, if it's only 1D, if M equals 1, it's not a PDE, it's an ODE, but if M is equal to 2, this formulation here is a PDE because you have theta 1 and theta 2, and that's a PDE here, right? So let me do the proof. It's a very simple proof. So if 4 holds, okay, and I define gamma of t, which is P of e to the lambda t, then by definition, gamma of 0 is P of theta, and gamma prime is equal to dp of e to the lambda t times theta. I differentiate the inside with respect to t, which is lambda e to the lambda t theta. And because I have because 4 holds, and because lambda is stable, then I map inside the domain. So this is in a smaller. This is in fact for theta in BM. This is going to be inside BM, and then I have the conjugacy relation. The equation 4 here, which we call often the invariance equation. And then because by definition, this is f of gamma of t. So then gamma solves the IVP, x prime is equals f of x, and x of 0 is equal to p of theta. But that's the solution of that by definition is phi of t p of theta, which is gamma of t, which is p of e to the lambda t theta, right? So then I proved that the conjugacy relation holds. And now if I want to go the other way around, that's the trivial part. If I suppose that 3 holds, then I just differentiate on both sides with respect to t. If I differentiate the flow, then I have f of the flow is equal to dp at e to the lambda t theta, lambda e to the lambda t theta, and I take t is equal to 0, and I get precisely equation 4. Okay, so this is now clear that instead of solving for 1, 2, and 3, then I can replace 3 with what I call the invariance equation, which is that PDE here. So now I do not have anymore the flow appearing in this equation, and now I can go and move on with using Taylor series representation. So now I'm saying that I'm using Taylor. Now, if F is analytic, then the data of that PDE is analytic. I have initial data. The Cauchy-Kovalevskaya theorem from PDE tells me that the solution will be analytic, so that I can use Taylor series representation to do that. Okay, so this is what we take as an approach here. So now we start with something slightly known and common. So now we have some equations to solve, and now we're going to plug some series ansatz into the equations and solve for the coefficients. Okay, so we'll do that with Fourier, with Chebyshev. Some people do finite elements. Here we're going to use Taylor series. It's very natural to use Taylor series here because we have data at 0, right? We have that P at 0 is X tilde, the derivative is A0. And so it's very local. So it's very natural, in fact. So this is the problem we want to solve. And then what we do is that we plug a power series representation. And in that case, each A sub alpha is in Rn. And now I have a multi-indices. I have multi-indices here because I have my, I have that I'm trying to parameterize an m-dimensional object, right? So here, alpha has m components. The absolute value of alpha here is the sum of the alphas. Theta, the parameters of the parameterization are in Rm. And here that notation is the multi-index notation. Theta to the alpha is theta 1 alpha 1 all the way to theta m alpha m. Okay, so from 1, what do I get? I get that A of 0 is in fact X tilde. If I just plug 0 here, then that's going to give all the non constant terms will go to 0, will vanish, and then that's my A0 is equal to X tilde. And from the second equation, then I have that AEJ. So EJ here is the jth element of the canonical basis of Rm. So it's basically, so if j is equal to 1, so that's A1, 0, 0, 0, 0. So that's equal to the jth eigenvector and so on. So these are my first order constraints coming from 1 and 2. And now, if I plug a power series in this, then if I take the derivative and I apply the derivative to lambda theta, then I will just get that the alpha coefficient in front of theta to the alpha is given by the dot product between alpha and lambda, where alpha lambda is given by alpha 1, lambda 1, plus all the way to alpha m, lambda m. Keep in mind that the lambdas are the stable eigenvalues, and the alpha i's are just the components of the multi-index. Okay, and the right-hand side is nothing else than the result of plugging a power series on that in my analytic map F. So for instance, if F is a polynomial vector field, which is not always the case, but if it is, then by plugging that power series expansion in the vector field, and I'm going to get Cauchy products arising from the nonlinear terms. Okay, so these three conditions now are put together to introduce a zero finding problem. Okay, this is how I do it. Now, maybe a quick comment is that there's a lot of different ways to solve, well, different ways. There's another fundamental other way to do it, which is to use the fact that Taylor series are local, and then when you think about, say, the nonlinear term here, if it involves Cauchy product and so on, then the Taylor coefficient of that term only depends on the lower order terms. Okay, so you can kind of write down explicit recurrence relation and solve them exactly up to some given order. Plus, of course, if you do interval arithmetic, the errors will propagate, but still there is an explicit way to write that down. And then at the end of the day, you have to bound the tail. Okay, so that's one approach. That's not the one I'm taking here, but that's the one that was originally used by many people. And of course, if the dimension of the manifold is very high, then that's a great approach. If the dimension is, I don't know, is maybe 2 or 3, then 1, 2 or 3, then and you don't want to take so many Taylor coefficients in the computations, and what I'm about to say is kind of quite useful. But keep in mind that the approach I'm proposing now is not the only one, and sometimes it's not the optimal one. But I like the presentation, so, and it fits in many other things I've been doing in the past. But as I said, the approach of solving recursively is also one, right? So what I do is that I present a zero finding problem. So I define A to be my sequence of all Taylor coefficients, all indexed by alpha, and f of A is now a map which is defined as follows. So f sub alpha of A is equal to A0 minus X tilde if alpha, if basically alpha is equal to 0, 0, 0. And then I define it to be AEJ minus psi j for alpha equals 1 with alpha equals EJ, the jth element of my canonical basis. So these are the first order constraint, which I impose on the first order level of f, right? And then the level f alpha, where alpha is greater or equal than 2, is given by alpha lambda times A alpha minus basically the the representation in Taylor of the vector field. So if I have a 0 of that map, then by construction, I have all the coefficients of my parameterization, which are satisfying this. And then I have, by the parameterization lemma, I have found a local parameterization of my stable manifold. Okay. So then I want to solve that in a Banach space. And now I have what? I have a sequence. Well, now I'm in Rn, right? So maybe a little bit of an abuse of notation. Here, A is indexed. It has many, it's indexed over alpha, but it is in Rn. So I can think of A as being A1, A2, up to AN, and each of them is a multi-sequence, right? Multi-index sequence. So my Banach space is L1. I just take L1 to the power n with norm in X to be the max of each of the components of the L1 norm here, and the L1 norm for one component of A is given by the following. So it's literally just the absolute value of the coefficients. So in this context, the C sub alpha are in R because I have assumed that my eigenvalues are real. So all this map is real, right? If I was considering complex valued eigenvalues, then I would just replace that by C, and then all of that would hold. But for the moment, as I said, I'm taking the simplest possible case. So that's my Banach space with that norm. And now I do something which is very common. Now I take the route of computer-assisted proof for looking for the 0 of a map on a Banach space. So then I take a finite dimensional projection of this. So say I go up to some order capital N, which is the Taylor order. So I take only my coefficients A sub alpha for alpha in absolute value going from 0 to some capital N. That gives me a finite dimensional projection. I keep only the same amount of map, and then I compute an approximate solution. So that approximate solution, I could compute it with the fact that I have a recurrence relation that I can compute explicitly, or I could just say, well, I don't care, I'm just going to apply Newton. And the nice thing here is that I know a priori that that solution, that problem, that PDE with these first order constraints, once A0 is fixed, it has a unique solution. Okay. So there's kind of a good reason to believe that, if you just apply Newton, since there is a unique solution, then it's going to work, right? It's going to, of course, may not always work, but in that case, it's not like there's a lot of different solutions and you could converge to something else. I mean, there's a unique solution. Of course, here the A0 is made of the eigenvectors, and you can play with their scaling, right? Because each scaling if you change the scaling of one column in A0, you still have a solution, a problem which will give you parameterization of the local stable manifold if the approach works, right? So once you fix these columns, then there exists a unique solution, and therefore, say even applying Newton, it makes sense, okay? But you could use recurrence relation. So that's the first step. The second step is to construct a linear operator that is acting as an approximate inverse. Again, here, if you're in a very high dimensional stable manifold, then you may say, well, this is way too much work. I will use recurrence relation and bound the tail. Fair enough. Because it could become a very, very large dimensional problem, right? So, and then once you have this, then you verify that this operator A is injective. You define a Newton-like operator about the approximate solution to be A minus A times f of A. Consider a closed ball of radius R centered at the approximate solution, and you show that you do have a contraction. And the way to do it is beloved Newton-Kantorovich theorem, which I'm simplifying it here. There's a lot of different ways to write it down, and then many people have different variations. In fact, this polynomial that we have here is reminiscent of what Michael Plum already did way before us. So anyway, so here I consider radius R positive, and I consider two bounds, a defect, which is the epsilon. So it measures basically how far the approximate fixed point to T is from itself. It's measuring A times f of A bar, which is basically the norm of T of A bar minus A bar. Okay, so that's a quantity we compute, and then we compute the operator norm of the derivative of Newton-like operator on the ball centered at the numerical solution. And that depends on R because that depends on the radius. We define this polynomial, which is the defect plus R kappa of R minus R. And if there exists a positive R such that is negative, then there exists a unique solution in the ball centered at the approximate solution satisfying f of a tilde equals 0. As I said, this we give it a name, but it's nothing else than basically putting all of these constants together and then having a nice little way. I think Michael Plum has the inverse polynomial in most of his papers. So if you look at this polynomial, then you can see that you cannot take R to be too small because then at 0, there is a numerical defect. Then if I was making, if that's my true solution here, then you can see it cannot be too small. It cannot be too big because then Newton won't be a contraction anymore. Newton is a local, works locally, right? It's quadratically converging, but if you're close enough to the fixed point, so if you're too far, then you may not have any more that linear terms are winning over the nonlinear terms. So then that just doesn't make sense anymore. So it really is local. So if you take it too large, you may lose contractivity. And yet there's a sweet spot. And that's what this polynomial is kind of encapsulating, right? So in practice, for solving the manifold, what I do is that I have my map F, I take a finite dimensional projection, I compute an approximate inverse, which I will show how to do in this very specific context. I build these bounds with interval arithmetic. The kappa of R here is used by using the fact that the L1 space that I presented is a Banach algebra under the Cauchy product. And I built some analysis, implement some operator norm bounds on the computer, combine that with interval arithmetic, build these constants in the radii polynomial, and hopefully prove that there exists a unique solution in the ball of radius R. Okay, so what is the operator in that case? The operator A. So if you go back to the actual map, that is the map for alpha greater or equal than 2, right? The ones for alpha equals 0 and 1 are trivial because I kind of trivially impose that the first component was the fixed point and the second components were the eigenvectors. So in some sense, this is really the identity when you think of the Frischia derivative. But then when you think about that, when you have the diagonal terms here when you take the Frischia derivative, and these terms are, again, if you have say polynomial vector field, then that's going to be taking the Frischia derivative will be lower triangular because these terms, they only depend on lower order term, right? So the operator really is, you can visualize it like that. And why does it stop here? These are zeros? Because I have only finitely many non-zero terms. So then at some point, this is just going to be equal to 0. Okay, so that's the exact, say, visualization of the Frischia derivative. And now, within that Frischia derivative, there is the derivative of the exact derivative of the finite dimensional projection. So here I did not even denote that before, but F superscript N is the finite dimensional projection. And as I said, the diagonal terms here, the lambda dot alpha dot lambda, they are here on the diagonal. Okay, that's 0. So what we do is that we say, well, because of, okay, that I did not emphasize a lot is that playing with the scaling of the eigenvectors can give us a decay rate in the coefficients of the power series representation. Okay, so what we do in practice is that we look at the data and then we adjust the length of the eigenvectors of each column so that there is a nice decay for the coefficient. Why? Because then that gives us more numerical stability. Okay, because in the proof after that, if you have very strong growth, but then you impose some decay in the Banach space, then you'll start multiplying big numbers by small numbers and things will become a little bit unstable. So what we do in practice is that we kind of adjust the weights, and there's a nice way to do it in the paper by, together with Maxime Reden, Jay, and I, we kind of have this way to kind of maximize the choice of the scaling to have what we want. Anyway, so once we choose that, we have some decay, and because of the decay, which comes from somehow the regularity, then these terms, they go to 0. And because they go to 0, we may say, well, I'm going to approximate the Frischia derivative by just this, right? I'm going to say, well, these go to 0, so I'm going to approximate it. And then I'm going to use my good old computer, take that finite dimensional matrix, plug it in my laptop, in that case, the computer I have in front of me will do that. We'll do that. I will do a live computation actually afterward. And then MATLAB, I use MATLAB, so it computes an approximate inverse A, and then now this is no longer lower triangular, this is full. And in the tail, oh, I say, okay, there's something here I'm missing, the inverse. So in A, this is the inverse of the tail here. There's something missing. Not happy about it. Okay. So here there should be something to the 1 over that in the tail. Okay. So that's my approximate inverse. And so now let me do one application to the Lorentz equation. Okay. So here are the Lorentz equations. I will take the two i's. So x tilde will be one of the two i's. I think I will actually do a live computation in MATLAB. So I think this is the one I will take, the negative I, we'll see. So the origin has a 2D stable manifold, and it has 1D unstable. So I said that I would present things for the stable manifold. So I'll take one of the two i's. And in that case, m equals 1, because at the I want to do just one-dimensional examples. So now the invariance equation becomes this ODE here, which I'm solving with power series. Okay, so then I just plug my power series. The first order constraints means that this, when k equals 0, this is the fixed point. When k equals 1, this is the eigenvector. So I have a stable eigenvector associated to the lambda, which is a stable eigenvalue. I match lag powers, and then this is what I get. I get k, so k replaces alpha here. So k lambda ak is equal to the resulting coefficients of the vector field that I obtained after I plug the power series in Lorentz. So I just take that, I plug that in Lorentz, and then I get the power series and I extract the coefficients, and this is the kth coefficient of the power series, where the star here are the Cauchy products. Okay, so now what I want to do is that I want to apply this machinery that I talked about. Now I have my map, now I apply Newton, and I will show you some computation. Okay, and the computation that I will do, they're using IntLab. I already started IntLab. Now I'm going to move to MATLAB. You see MATLAB, right? Okay. So what I do here, so I choose my parameters in the Lorentz equation, the classical one, and I choose in that case a fixed point. So I got here the negative I, and I want to do a one-dimensional stable manifold. So let's say I will start with a modest computation. So let's say I will take maybe 10 Taylor coefficients, and I did my computation so that the eigenvectors have length 1. Okay, and then I can play with the scaling in that case. So I'm going to take I'm not going to take any scaling. So it's going to be 10 Taylor coefficients, and I'm going to take the length of the eigenvector to be 1. And what I do is that I apply Newton to the map F, which is the one that let's see. That's my map F, which is the zero fighting problem for Lorentz. So these are imposing first order constraints. This is the eigenvector, and then this is nothing else than the map, right, with Cauchy products, and that's building precisely what I want here, right? I want that minus that to be equal to 0. So that's exactly what the code does. And then I'm going to run the code. I'm going to apply Newton to it. In that case, I just impose at initial condition for Newton. I impose that all coefficients are 0, but the fixed point is fixed, and the eigenvector is fixed. Okay, so let me apply Newton. So then, you know, it was not the best defect at the beginning. I started with that, but then you could see that Newton converged very quickly. And in that case, well, I will. Okay, so that's my global attractor, and you can see that if I move my, so I have something very small, right? This in red here, it's a very small manifold, and the rigorous error bound here is 10 to the minus 17. Okay, so it's a very simple computation. But if I wanted to do something more interesting, then what I could do is that I could take more Taylor coefficients and take a much bigger scaling of the eigenvector. So let me redo that now with this. So what I can see here, by the way, are the Taylor coefficients, of each component of the parameterization. So you can see the decay. Okay, there's still decay. It gets all the way to 10 to the minus 12 for the Z component. The rigorous error bound that I get is 10 to the minus 12, and that's now the image of the 1D stable manifold of the I. So you can already see that it is much bigger, right? This is like, and the real stable manifold attached to the I is 10 to the minus 12 away, because in these, when we choose the L1 norm as a norm for our Banach space, that provides us a rigorous C0 upper bound for the location of the object, right? So you can see here that this is kind of more satisfactory, right? This is more satisfactory. And if I was even more, say, ambitious, then I could go to 100 Taylor coefficients, maybe take a larger scaling, and then, yeah, I still have a success here. So now the rigorous error bound is 10 to the minus 8, but it's still kind of it's still bigger, right? So now these are really, really large objects when you compare. So you see that, huh? Yeah. So this is probably the simplest possible example to share. And these were live computations with IntLab, right? And then, yeah, they're kind of fast. I mean, I had to kind of, I mean, this is the code for the bounds, right? The y0 is basically my epsilon, and then z0 plus z1 are like the kappa of R incorporated. So we often like to have these bounds split. The kappa of R, we split them in a couple of different ways. There's a lot of ways to do it, but we often have, at least in my field, like this way to write down these bounds as a sum of some z1, z2, and z0. Anyway, so that's kind of the application I wanted to do in details. And now I want to very quickly finish with other applications, which are, say, a little bit more ambitious. So I mentioned before that we can do parameterization of stable manifolds of periodic orbits or unstable manifolds. So I'm not going to talk much about the details, but what you have here are the three equivalent conditions to impose for the parameterization method of a stable manifold of a periodic orbit. So the first order constraint is that you're looking for a parameterization which depends now on two parameters, on T and sigma. And in T, it's going to be the periodic direction, and in sigma, it's going to be the Taylor direction. And the first order constraint is that when sigma is 0, you are at the periodic orbit gamma of T. And when you differentiate with respect to sigma, and you evaluate at sigma equals 0, then you have the stable bundle, which will be, in that case, that's an example for one-dimensional stable manifold. So that's basically the eigenvector, the whole linear tangent space to the manifold, right? You can solve that using Fourier series and by solving the linearized problem. That's the second equation here. And then the third one, that's the conjugacy relation, which you see as a cartoon downstairs here, okay? So the linear dynamics is given by T prime equals 1. So basically in time, the linear dynamics is just the rotation. And sigma is lambda sigma, where lambda is the stable eigenvalue. So in that picture, I'm making that so that it's only a one-dimensional stable manifold. If you had more dimension, then you would have to have more terms here. You have a lambda 1 all the way to lambda m, and then sigma would be sigma 1 to sigma m, and so on. But basically, this cartoon picture here it tells you that the dynamics in parameter space right now is topologically equivalent, or it's conjugated, sorry, to the dynamics on the stable manifold. So what you can do is that you can take the power series, you plug that in your equation 3. F is your vector field. Now you get to solve for the Taylor Fourier coefficients of a system, but the same method applies. You have a map, and then you can look for the zeros of that map. Again, there's an equivalent of, you could also solve that recursively. You would have to solve layer by layer in Taylor. You would have Fourier problems to solve, but that's definitely a possibility. And then we apply that to compute stable manifolds in the Lorentz equation. This picture on the right is not quite a proof. I think the proof is slightly smaller than that, but I still like it. It's one of the first beautiful proof. This was my most beautiful picture ever when I had it, when I published that with Jay, so I still like it. And Jay did that with Poveri. So this is the stable manifold of the stable, right? Yeah, the red one is the stable, yeah, of the periodic orbit, one of the periodic orbit in Lorentz in the chaotic attractor. We also apply that to finite dimensional projection of Kuramoto-Shipashinsky. This is not a computer-assisted proof, but that could be used as an input for computing stable manifolds of periodic orbits, which for the moment the parameterization method does not readily apply. But these are applications. And oh, I guess this slide was not supposed to be there. Then together with Olivier and Jay, we considered the delayed van der Pol equation, where we fix these parameters here. So I'm going to go quickly because I want to have maybe 2 minutes for questions. And in that case, we look for a parameterization which depends on the Taylor dimension. In that case, it's going to be 2. And it depends on the history. And these are the constraints that needs to be solved for the parameterization method of the unstable manifold. C here is just a steady state. In that case, it's 0. And we plug now a power series expansion again. But in time, it's known what it is. So we don't really have to solve for that. We just have to solve, say, for the expansion in time is this one. So we just have to solve for the Taylor direction, the A sub alpha. And that's the power series expansion that we plug in equations 1, 2, and 3. And then again, we have a zero finding problem, or we use recurrence relations. And then we can get this beautiful picture here, which is a proof. So what you have here is that in green, you have the unstable manifold of the origin, and you can see that how it sits in the global attractor of the delayed van der Pol. And in that case, we used, so it was a 2-dimensional computation, so n equals 60, and we had a rigorous error bound of 1.3 times 10 to the minus 13. So the true unstable manifold is 10 to the minus 13 away. And well, this is what Jonathan and Jacquette has in his talk, so I'm not going to talk much about it. That's my last application. So here we have the nonlinear Schrödinger equation, and we wanted to study the global dynamics. And in order to do that, we actually computed non-trivial steady states, which we proved with a computer. And we computed rigorous computations of the unstable manifold, which we then used to actually integrate forward in time, which is what Akitoshi's talk is about. So using the method of Akitoshi's talk, then we can take the endpoints of the manifolds, integrate them forward, and Jonathan Jacquette then developed a method to compute rigorously an enclosure of the center stable manifold, and we can have global existence of solutions in the nonlinear Schrödinger equations, which is something that just appeared in Advances, actually this month. So I guess this is it for me. I took a little bit, only 1 minute for questions, but I'm sorry. Yeah, I will stop here. So thank you very much for your attention.
Thank you so much. Wonderful talk. So comments and okay, question now is it's open for questions and comments.
May I ask about the normalization of the eigenvectors which you mentioned? So,
yes. Sure.
So what you did in the program, you normalized all the eigenvectors with an equal factor.
Well, in that case, it was a one-dimensional example, so there was only one rescaling.
Only one. Yeah. So, yeah. But so you have a lot of parameters when you when you want to optimize the scaling. So you have for each eigenvector you may have a different scaling, and if you have multiple eigenvalues, you have even more. You have eigenspaces where you can choose. And how to do that? You said it's optimized. You do that in order to optimize the decay. Is that just by trial and error, or is there some systematic way of finding the optimal normalization?
Yeah, so I mean, it also depends on what we want to achieve, right? Because sometimes we have, say, an unstable manifold and we want to kind of have a larger image in some specific directions. So say if I'm after a connecting orbit, and I know that the connecting orbit is kind of going to live in some portion of the stable manifold. So I may want to kind of get directions, longer directions in some different, I may want to optimize some directions, right? So that could be another way to choose about the scaling. That's one thing. After that, if you want to have like you have to, often what we do is that we do this least square fit. And then say you want to have some sort of, in 2D, you would have a 2-dimensional surface of decay. And then you may want to have like similar decay in the 2 directions, right? So then you kind of, you can set up your scaling. So that's the nth term, because it's in 2D, you have alpha equals 0, and then alpha equals 1, alpha equals 2. So you may want to adjust your scaling so that the nth term of your Taylor expansion, if you take the norm, the L1 norm of the nth order terms, and it is, say, 10 to the minus 16.
Okay.
Right, that's one possibility. But the possibility, the other scaling that the other choices can be made as a function of what you're trying to achieve with the manifold. Because if you take the scaling, then you may have much larger portion, and then you may not care much about that. So depending on which direction you want to favor, then you may do your computation accordingly.
Okay, so it depends on the goal, I see.
Yeah.
But by the way, do you get some explicit information about the convergence radius of that power series after all?
Yeah, we do. But the thing is that we choose the Banach space to be L1. So the ball is the unit ball.
All right.
Right. So, and that's actually this game with the decay rate, right? Because we choose the decay rate so that they decay. If we did not impose anything, they could grow super fast, but then the ball would be smaller. Right. So the choice of doing the proofs in L1 is really a numerical kind of stability type of choice. And the proof after that will always be that the radius of convergence is 1.
All right. Thank you.
Okay. Other questions or comments? Okay. If not, yeah. Okay. Thank you for graphing. Okay, Jonathan.
So we used Taylor methods in the talk today, and I was wondering how essential is analyticity for the parameterization lemma?
For the parametrization lemma, and you mean the equivalence between?
So do you need an analytic?
No, because you need differentiability, right? You need to be able to to take the derivative of p, and when you pass to the limit inside. No, yeah, that's the previous result. No, I don't know. I mean, if you go back to the actual setup.
It's Raphael's paper too.
Yeah. Let's see. Where is it? Where's the lemma? It's here, right? So yeah, there's absolutely nothing there that requires analyticity, right?
Mm-hmm.
Yeah.
Has there been work applying the parameterization method for non-analytic?
So I think this is
fields?
the second paper. Yeah.
Okay.
I think that there is theoretical results, but in practice, the thing is that these objects, when they are high dimensional, then what kind of basis do you use, right? So that's why I was saying before, these three conditions here in that formulations are so naturally going toward Taylor that so the work you did with on splines, did you assume could you have done that without assuming analyticity? Yeah. So basically, if you have, but then you have to use splines and you have to use different type of basis, right?
You just do Taylor up to the order that you have derivatives. If Jonathan produces a C10 vector field, then you can only do Taylor up to order 10.
Right. Yeah. I guess as far as I'm concerned, I only work with analytic problems, but it's definitely, it looks like there's quite a few directions to take where it's not analytic.
I think when it's non-analytic, then you just have to find another method to solve the PDE for the parametrization.
Absolutely,
that's the consequence.
Right.
Mm-hmm.
And I talked about Koshikov-Vereskaya, right? So basically, the solution is kind of as smooth as F. So yeah. So if F is only C3, then yeah, you may have to use different bases. Or as Jay said, you can go up to order 2 in Taylor, and then after that bound the remainder using something else.
Okay.
Thank
Another
you.
question?
Nice talk.
Okay. Another questions or comments? Okay. If not, okay. Thanks for Jean-Philippe again.
Thank you. Thank you, guys.